Our first speaker this morning is, of course, Vinton Cerf. I forgot to ask Vinton if he's the origin of surfing the internet, but we'll assume that that's the case. His list of accomplishments is certainly too long to read in this forum, but as I mentioned earlier, he is the co-designer of the TCP/IP protocol, which all of you know is really the foundation of the internet, and other key design principles that underlie the architecture of the internet itself. He was chief technical strategist for MCI, and of course he's currently the chief evangelist for Google. His list of awards is equally long. He received the U.S. National Medal of Technology in 1997, the Turing Award, which is effectively the Nobel Prize for people in computer science, in 2004, and the Presidential Medal of Freedom, which is the highest civilian award available in the United States, in 2005. So it's my really fantastic pleasure to introduce Vinton Cerf to share with you his ideas this morning. Thank you.
There we are. Well, first of all, thank you very much for a nice introduction, Ron, and a lovely dinner last night. I'd like to suggest to you that the term geo may be overly Earth-centric, and that I hope that as you think your way through some of the problems that you have to address, that you won't limit your architectural designs to simply Earth-centricity, because we're already rapidly gathering a great deal of information, as I'm sure many of you know, around the solar system. So I hope that you can think in interplanetary frameworks, which is what I'm doing with the Jet Propulsion Lab. There is an actively ongoing development of an interplanetary extension of the internet. The protocols are ready to go. We're going to be space qualifying them by 2010. So I hope that the GeoWeb concepts will catch up with us by that time, so that as we deploy this interplanetary backbone, your data structures and architectural notions will be compatible. Let me say that it's a little daunting to do this in 20 minutes, and I also have to warn you that some of these ideas may be half-baked. As a result, I won't be offended at all if you either burst out laughing or suggest that I should exit the room. So these are just ideas, and I'm trying to find out, in fact, from you whether or not any of them make sense. I thought I'd start out by just showing you what the predecessor to the internet looked like. It was a 4-node system in 1969, and I was a graduate student at UCLA, and I got to program that Sigma 7 down in the lower right. That computer, and to put the first computer onto the ARPANET, that computer is in a museum now, and I suppose some people think I should be there along with it. If you fast forward to 1977, you discover the very first time that 3 different packet switch nets were interconnected. And I know you can't actually read any of that, but there was a mobile packet radio net, the wireline ARPANET, and a shared packet satellite network, all of which operated differently in detail, although they were all based on the same notion of packet switching and sharing of common channels. So that's a very important milestone, and we'll celebrate the 30th anniversary of that first 3-network interconnection later this year. If you fast forward to 1999, this is pretty much what the topology of the internet looked like. All you can tell from this is that it got bigger, it got more complicated, and it got more colorful. And I think that's about as good a description of internet as anybody could come up with. I'm going to try to do something here which is pretty dangerous. I'm going to try to pick out some important architectural elements of the internet and ask whether we can project those ideas onto the GeoWeb notion. And I don't know whether this is reasoning by analogy. It's always dangerous, but I thought it would be worth a try. To explain the T-shirt, when Bob Kahn and I were doing the 1973 design of the internet, we knew at that time that we did not know what new technologies were going to come along for transmission and switching, but we really, really wanted the internet to be future-proofed. We wanted it to operate on any new transmission and switching technology that came along. So when we designed the internet protocol, we said that we wanted it to be essentially independent of the underlying transmission system, and that's pretty much the case. The internet packets don't really care how they're carried. It could be on a fiber or a satellite link or a radio link or a twisted pair or Ethernet. So all of the new transmission and switching technologies that have come along since 1973 have basically been able to carry internet packets. So I had a t-shirt made that said IP on everything, and that's basically what I've been doing for the last 35 years. Once you end up successfully deploying a standard like that, then people start assuming that it's there, and they start building other protocols on top. And so I need a new t-shirt now that says IP under everything, because that's basically what's happened, is that all these superstructures have been added. There's another characteristic, though, of this internet protocol layer, which separates the application world from the underlying transmission technology. The packets not only don't know how they're carried, they don't know what they're carrying. It's just a bag of bits at the internet protocol layer. And that's turned out to be a really important notion, because it says the network doesn't understand anything about the applications that it's supporting. That was a very deliberate design choice. That means that it's only at the edges of the internet that there's any interpretation being done of the contents of the packets. That has allowed people to invent new applications and put them up on the net without having to get permission from anyone, without having to get the network to change. It's just the interpretation of the bits that counts. So that led to this notion of end-to-end principle, which says that basically it's the endpoints in the net that imbue the packets with meaning. The architecture of protocols in the network is layered. You can think of it like a staircase, if you like, or a multi-story building. The idea here is that the lower levels of protocol do things in common, and the higher levels do something that's specific to that protocol. And you can stack these things up. As the higher up you go in the protocol layer space, the more specific the information is at that protocol layer. In the case of the IP layer, the most important thing that Bob Kahn and I introduced was a common address space, so that regardless of the number of networks that were connected together in this network of networks, there was a way to say globally where a termination point was, to identify a termination point in the network. It's not a geographical identifier, it's a topological identifier. But it was a common space of identifiers that everyone could use to refer to an endpoint in the internet. And so that was an important conceptual element in the architecture. I did make a mistake, though. I only allowed 32 bits for identifying unique terminations in the net, and that's only 4.3 billion terminations. That decision was made in 1977. And at the time, I thought for an experiment, 4.3 billion terminations ought to be enough. Well, 30 years later, it's clear that it isn't enough, and so we were going to have to move to what's called IP version 6, which is 128-bit address space. That's about 3.4 times 10 to the 38th addresses. And I used to go around saying that that's enough address space so every electron in the universe could have its own web page. Until I got a note from somebody at Caltech, "Dear Dr. Cerf, you jerk, there's 10 to the 88th electrons in the universe, and you're off by 50 orders of magnitude." So I don't say that anymore. What is important, though, and the thing that I want to draw out of this part of my discussion, is that as we go up the layers of protocol in the internet, you find that each one of them adds some new concept. So in the case of the IP layer, basically it's packet transport, no interpretation of the packet's contents, and identification of source and destination. That's it. The next level up has protocols like TCP, the Transmission Control Protocol, or UDP, User Datagram Protocol, or RTP for Real-Time Protocol. The TCP tries to keep the packets in order. It tries to recover from duplication by throwing copies away. It tries to recover from packets that are lost by retransmitting. It tries to do flow control. So it is, in fact, introducing or inducing a relationship among the packets, in this case, a sequential one. In the case of UDP, there is no sequential relationship at all. It's simply like postcards. So there's no guarantee